This is Group 1, the Lower Body Exoskeleton Project. We are Thomas, Caden, Chris, Ford, and Musa. Our sponsor for this project is Florida Power and Light, and our advisor, Rich, comes from the Department of Mechanical and Aerospace Engineering for this project.
The lower body exoskeleton suit that is sponsored by FPNL is intended to alleviate the exhaustion and health concerns of lineman workers by assisting them with ascending and descending of wooden power poles. The primary material the exoskeleton will be composed of is 6061 aluminum. The knee and hip joints of the frame are being connected using a ball and socket mechanism, as well as the hips having an additional hinge mechanism to support rotation. For the purposes of this demo, we will be demonstrating three of the constraints. The first being constraint 1 regarding the locking mechanism, constraint 3 regarding the safety system, and finally constraint 7 regarding the hyper torque generation.
As stated, one of the specifications is the safety system. The safety system is to protect the user in case of failures. The specification states that there must be a reaction time of less than 0.5 seconds, withstand an impact of 50,000 newtons, and a fall distance of 36.6 meters. Much of the safety system is mechanical. As you can see on the bottom are many of the stress tests that the system was put under through the ANSYS system in order to make sure it can withstand these falls. But there is a large electrical component as far as the safety system goes. An important part to understand is the sensors. The sensors are Excel gyroscopes, one place at the top and one place at the bottom of each joint, and these are used to calculate the constantly changing angle of the joint. In this demonstration, you can see the joint going from 180 to 90 degrees and the angle of the joint being measured as it takes the step and reacting properly. This allows the motors to react to the steps being taken by the user using conditionals set in the program. The sensors also allow for the safety system. This is the software used in order to calculate the angle. And then this is the fall detection system in the sensors. The sensors are using the total acceleration in order to detect a near free fall. Again, this is used to help protect the user in case of any type of fall. When this fall detection system actually detects that the user has fallen, the program will stop running the motors, sensors, and any other peripherals until the system is completely reset. The system can be completely reset using a button that is attached to the Arduino, and the software for this can be seen on the left. The demonstration shows that as soon as the joint is dropped from around 8 feet in the air, the whole system stops until it gets reset as it is supposed to.
Spec number 2 is the torque requirement. The minimum torque required being 10 Newton meters is the lowest level of torque acceptable to help the user. Given that our motor is only rated for 8 Newton meters of torque at around 800 RPM, we had to figure out a way to amplify the torque without putting more load on the motor. So we decided to utilize a 1:4 gear ratio with a belt and pulley system. This allows the device to quadruple the amount of torque being produced by the motor after the joint. We constructed a bench test setup to help prove our math and experiment with different loads. Unweighted, using 140 watts at 325 RPMs, the motor put out 4 Newton meters of torque and amplified this to 16 Newton meters after the pulley. And as you can see, testing with a 2.5 and 5 pound weights, we found if we maximize the amperes, upping the power, we could get 8 Newton meters out of the motor and 24 Newton meters out of the pulley. Here is an example of how the experiment was conducted.
third specification given to us by FPL consists of a locking mechanism. This locking mechanism will consist of an electronic part and a mechanical part. The electronic part allows us to lock the motor to a certain angle by feeding it in the current angle when the locking mechanism is activated and comparing it to any future angle in order to provide current and torque in the desired direction. The mechanical angle of the locking mechanism is a gear that is going to be mounted to the knee joint, and a barrel bolt will be slid in between the teeth to prevent the knee joint from moving. The next section outlines the progress that we've made in other key areas of the exoskeleton's development. This Gantt chart outlines the current projects that we're working on, as well as the projects that we have finished. Currently, we are working on the subsystem integration, the motor housing, the battery pack, as well as the power system. We also have outlined the conference papers, the demonstrations, and any sort of documentation that we are needing to provide. One of the next steps for integrating our design into the mechanical engineer team's design is to mount the motor on the knee joint that they've provided us. We've had to add a couple key features in order to utilize our design with their design. The first one being the motor mount with slots in order to move the mount back and forth to tension the belt. A adjustable thigh mounting that can contract and expand depending on the size of the user, as well as a metal locking piece to prevent the knee from overextending. This is all in addition to the pulley that was integrated in the benchtop setup that we have done testing on.
Now to discuss some feature changes, with the first being about the motors. Given that the knee motors are capable of providing a sufficient amount of force to assist the average user, it is no longer necessary to incorporate motors at the hips. Therefore, the use of hip motors can be removed, as the knee motors are capable of fulfilling the necessary requirements of aiding the user. This decision has simplified the design of the exoskeleton and reduced its complexity, cost, and overall weight. Ultimately, only having motors at the knees can simplify the user with more than enough force. The next big feature change is about the batteries that we will use. It has become incredibly challenging and expensive to obtain specialized batteries for this project. As a result, it has become more practical to utilize readily available and affordable batteries from a well-known manufacturer such as DeWalt. DeWalt batteries are widely used in various industries and are known for their reliability, durability, making them our first option during this transition. Another great benefit to using DeWalt batteries is that we will have the advantage of being able to use an adapter that is easily connected to the battery and provides wire terminals for connection to the exoskeleton. The photo on the right shows the adapter, and this eliminates the need for any specialized connectors or complex wiring, making the connection process simple and straightforward. Now on to the power system. We just needed to make sure from our benchtop testing that we had accurate numbers to ensure that we could provide enough power to the system to last for at least 1 hour. From our benchtop testing, we ran multiple tests, and it was shown that just for 1 hour, the amount of current needed after 5 minutes was only 66.67 milliamps per hour. If we multiply this to show this for the 1 hour, the total comes out to 0.8 amps per hour, and if you add this to the other battery, it came out to 1.6 amps per hour total needed for 1 hour of use. The remaining 0.4 amps from the battery will be more than enough to power the rest of the peripherals such as the sensors and the boards. Now on to the remaining challenges. The last major challenge, as you can see from the image on the right, is our final assembly without the straps. The challenge here is to be able to properly mount the motors and the peripherals in a way that they'll be safe and secure. The motors will need to be protected from the outside elements and also be waterproof. The last major challenge is properly securing the battery pack. This is the challenge as the motors because they must be secure and in an environment that won't be wet to avoid any accidents or shorts.